All right, in this video, I want to explain the idea of type 1 errors and type 2 errors in null hypothesis significance testing. In other words, anytime you're doing a statistical test of the sort that gives you a p-value and you're comparing that p-value to a threshold like 0.05 to reject a null hypothesis when the p-value is low enough, that's what we call null hypothesis significance testing. And when a p-value is low enough, when it's really unlikely that we'd see a sample like ours if the null was true, then we reject the null, right? But even if the p-value is a low number, it's never zero. So it's always possible that we would get extreme results like ours even with a true null hypothesis. So the whole thing, the whole procedure is probabilistic. We are calculating and finding something to be quite unlikely, but that does leave open some chance that the unlikely thing happened, that the null is indeed true, and yet we got the sample result we did. So it's important to recognize that the chance of the null hypothesis being true, it's never actually zero. Even if it's super unlikely to get a sample mean this extreme, as extreme as ours. In other words, our sample is way out in the farthest bits of the tail of the critical region, it is still possible the null is true. Now, with such very small odds, we definitely should reject the null hypothesis. It is the right choice, the right conclusion to come to. We just have to accept that sometimes our conclusion might be wrong. Another way to say that, it's still a really good bet, even if your bet happens to turn out wrong this one time. So what does it mean for our bet to quote-unquote turn out wrong? It means even if we follow our best procedures, do your stats properly, our final conclusion can sometimes not match with reality, and it can happen in a couple different ways. So the first way is what we'll call a type 1 error. This is when we get a low p-value, lower than our threshold, so we do reject the null hypothesis. We've done all the proper stats, and we properly concluded that we should reject the null hypothesis. But in this case, in reality, the null happens to be true. That would be a type 1 error. We often call this a false positive because it means you're going to conclude that there's a statistically significant effect or conclude that there's a difference, even though in reality that doesn't turn out to be true. Now, how likely is it that this will happen? We actually have a good idea of that because that is what we're choosing when we choose our alpha level. When we choose the cutoff that will consider a p-value low enough to reject the null, usually 0.05. So the probability of a type 1 error of a false positive is equal to alpha. So the convention here is we use an alpha level of 0.05, meaning we accept a 5% chance of a false positive, a 5% chance of a type 1 error. So if you instead chose to set your alpha value very high, like 0.30, it might make it a lot easier to get a quote-unquote statistically significant result, but it also means 30% of the time when the null is true, you've mistakenly rejected it, which is not great. Now, on the other hand, if you set your alpha value very low, set your cutoff real low, like 0.0001, which is 0.01%, then you'd be playing it really careful and conservative, and that's great, but then you'll only reject the null for very, very, very extreme samples, which means even if the null hypothesis is true, if the null is true, then 0.01% of the time you will get a sample mean extreme enough to reject it, even though the null is really true. That's a pretty low false positive rate. You won't really have to worry about false positives at all if you use such a wildly tiny, super low alpha level. But in the trade-off, it also means you will almost never get a statistically significant result. You just set the bar for a significant effect at a level that's too hard to reach with normal evidence. And that's why we usually use that middle ground, the conventional value of 0.05 for the alpha value. We accept a 5% chance that when we find a statistically significant result, it'll be a false positive. At which point we just have to do replications and repeat our studies to kind of double check and become more confident over time. Now, the other issue that can arise is what we call a type 2 error. And I want to be clear here. We are not saying error like you made a slip up or a mistake. This is stuff that can happen even when you follow perfect statistical procedures. It is literally built into significance testing because the whole thing rests on a probabilistic basis. So it is not an error in the sense of a screw up, but a type 2 error means you did the stats properly, and in this case, the p-value wasn't below your alpha cutoff, so you did what you're supposed to. You fail to reject the null hypothesis. In other words, you conclude there's not a statistically significant effect found, but in reality, the null happens to be false, and there is an effect. You just didn't discover it. So basically, you didn't find enough evidence to reject the null. You didn't find enough evidence to conclude there's a real effect or a difference, even though in reality there is. So basically, you missed it through no fault of your own. So another term for type 2 error is a false negative. Because the conclusion you came to, what your stats test led you to conclude, was a sort of negative result. Like you don't think there's anything going on here based on the p-value not being low enough. But in fact, your result doesn't match reality, and there is an effect. Or another way to put it, we did the proper statistics, and our sample mean was just not far enough out to be in the critical region, so we didn't reject the null. But this can happen simply because we'll never perfectly detect effects or differences in the world. We just can't detect everything. And it's especially going to happen a lot if maybe there's a very small effect, which is hard to detect, or if we used a really low sample size, a low n, which made our distribution of sample means too wide, like that graph where we draw the rejection region. That'll be too spread out to make it easy for a sample to fall in the rejection region if we have a small sample size. Now, we can quantify the probability of a type 2 error, although it's a little harder than a type 1 error where we just picked the number. With a type 1 error, it was literally just the alpha level that we have control over. We get to choose that. Usually, though, we'll use 0.05, right? So usually, type 1 error is a nice predictable 0.05, or a 5% chance of a false positive. But what are the odds of a false negative of a type 2 error? So we're going to call this, we'll call it the beta level, just using the Greek letter beta. And we know a couple things about it for sure. So first, the beta level is always going to be inversely related to the alpha level, just meaning the bigger the alpha level you choose, like if you choose a big one like 0.1 instead of 0.05, you will get a smaller beta level. And if you choose a smaller, more strict alpha level, like a cutoff of 0.0001 to call something statistically significant, then that'll mean you also get a much bigger beta level. So there is a trade-off here. The more that you leave yourself open to false positives, the safer you are from false negatives. And the more you rule out false positives and make them unlikely, the more chances that you'll miss a real effect and end up with a false negative. But also, the beta level is influenced by sample size. So regardless of what alpha level you pick, there are other ways you can help make your beta level not be so bad. So if you use a gigantic sample size, you're just much more likely to detect any effect that happens to really exist out there. Like, regardless of everything else, a big sample can help protect against false negatives and ensure you do find any effects that do exist out in the world. And there are other things that go into the beta level, like whether the effect you're trying to discover is a tiny effect or a big effect, right? That'll make it more or less likely to detect the effect. And also, just how much variability there is in the variables you're measuring. Like, is there a big variance, a big standard deviation in the stuff you're measuring, or not much at all? All of that can affect the beta level. What we're really talking about here is the chances you will find or miss an effect that actually exists in the world. So maybe another way to look at type 2 errors and the beta level is to think about what it would mean to successfully detect an effect that does exist out in the world. And indeed, you'll often see researchers talk about the power of a study. And this is the probability that we will correctly reject the null hypothesis when it is in fact false. In other words, the probability that we'll get a low p-value will declare a statistically significant effect when there is indeed a real effect. So power is good. In fact, power is the opposite of beta. It is the opposite of a type 2 error. If there is a real effect in the world, a real difference between your medication group and your control group, or a real difference between men and women, or whatever, then power is the probability that your statistical test is going to reject the null, and you'll be able to declare, I found an effect. Whereas beta is the probability that you'll fail to reject the null and miss that effect, not find it at all. Together then, power and beta, they add up to 1, to the whole probability space. You could say power is equal to 1 minus beta, but that also means you could say beta is equal to 1 minus power. Same thing, they just add up to 1. They add up to being the only two possibilities when there is a real effect in the world. You either find it or you don't. And some probability comes into play with which it is, whether you find it or you don't. But we can shift those probabilities so we can get better power, and thus lower beta, by doing stuff like choosing a less strict alpha level. That's one option. It's not a good one. It's not a good option because we usually want to stick with that 0.05 unless we've got a good reason to change the alpha level. But also you can use a bigger sample size. And this is usually the best way you can increase power, and in doing so also decrease beta. As long as you can afford the time and the cost, a larger sample size is basically always better. Now, I suppose you can also just try to find, isolate, and test for, try to study large effects rather than tiny, subtle effects. That will, in fact, make it more likely your statistical test will come out statistically significant for any effects that do exist. And you can also do things like minimizing variance, minimizing standard deviation in your samples, which basically it's like decreasing the noise, making it easier to find the signal among that noise. And this can be done in lots of ways, like, for example, using a within subject design, where everyone serves as their own identical control rather than between subject designs. But also you can try to keep everything extraneous in your study kind of really similar between your conditions. Try to test on the same days and in the same place and using a measurement instrument that is really precise. Things like that. But basically, some combination of the things on this list can be your way to get a good power level and make it likely that you will find any effect if one exists. And again, the basic idea here is if the null hypothesis really is false in reality, our stats test is either going to reject it, which is great, we found the effect, and the probability of that is 1 minus beta, or our stats test will fail to reject it, which sucks. That's a false positive. And the probability here is beta. Sorry, a false negative. It's a false negative. So just to test yourself here, if I calculated the power in my study at the sample size I'm using, I calculate the power to be 0.72, then what is beta? What's the probability of a type 2 error, of a false negative? So pause and answer before moving on. And since it's just 1 minus power to calculate beta, we'd say 1 minus 0.72, so beta is 0.28. In other words, we had like a 72% chance of finding the effect when using the sample size and the study design we had, but that means we also had a 28% chance that carrying out our study and doing the stats properly, we would still fail to detect the real effect. Now, if you find this stuff confusing, sometimes it can help a lot to lay it out in a table like this. So on the one hand, we can say that reality is one way or another. So in reality, whether we know it or not, the null hypothesis is either false or it's true. That's just how the world is. If the null is false, then there's some real effect that exists, a real difference between our groups, a real effect of the medication. But if the null is true, then there is no effect, and any differences we find in our samples, like between treatment and control, are just due to chance, to random sampling. But that's the reality of the world up here in this kind of orange font. Either there's an effect or there isn't, regardless of whatever we think or conclude or do stats on, okay? But we also are going to, indeed, run our statistics test. We're going to use whatever sample size and whatever research design that we did, and it's going to lead us, when we run those stats, to one of two conclusions, right? Either we're going to reject the null hypothesis, meaning our sample was in the critical region, our p-value was below that alpha cutoff, or we fail to reject the null because our sample was not in the critical region, like our p-value was not low enough, so we fail to reject the null, we leave it an open question. This is what will happen anytime we run a stats test and get our p-value right. It's going to be one of these two things. Now that means together here, that's going to leave us 4 possibilities that can happen anytime we run a statistical test. So when the null is false, we might reject the null, which is great, right? Sometimes this can happen. The null is false, we reject the null. That upper left box is awesome because it means we found a real effect. We reported a statistically significant effect, and sure enough, we got it right. Or for that matter, the null might be true and there's no effect in reality, and we might run our stats and thank God we failed to reject the null hypothesis, which is also great. In that case, our statistical results match up with reality as well. And certainly, both of these boxes should be the most common that happen if we're doing science correctly and using a big enough sample size and good research designs and solid research practices. But there are 2 other possible things that will sometimes happen regardless of what we do. The upper right box is where the null hypothesis is true. So in reality, there's no effect, but we ran our statistics and we rejected the null. Maybe we even published our work and put out a press release telling people about the effect we discovered or the difference we discovered. We tell people it's statistically significant, which it is since that's what our stats result was. But we just have to remember that sometimes that means a type 1 error happened and it's actually a false positive like this box here. And of course, like in the bottom left box, we can get a type 2 error. In that case, the null is false, so there is an effect out there in the world. But our stats test told us that we failed to reject. So we don't think there's an effect, or at least we don't have good evidence of it. We don't have good enough evidence to conclude that there's an effect. Even though there is one out there, we just haven't detected. And as we already saw, what the odds of each of these boxes are, we have an idea of that, or we can calculate that, right? So let's look at the rightmost column here. So that's when the null hypothesis is true, when there's no effect. As we can see, in that case, we have our alpha level, because that's the thing we chose, right? Usually 0.05, that is the odds of a type 1 error, the odds of that box. And that means the bottom right possibility is 1 minus the alpha level. Like if alpha is 0.05, meaning 5%, then we have a 95% chance of not rejecting the null when the null is true. That's great. We have a 95% chance of avoiding a false positive. But look at the leftmost column then. This is when in reality there is an effect. The null is false. There is an effect. In that case, power and beta have to add up to 1, right? These 2 possibilities have to add up to 1. They have to cover the 2 ways our stats test could go when there's a real effect out there. So we quantify beta as our chance of a false negative, where we didn't reject the null, we missed the effect. And power is the odds that we did find it, the odds that we rejected the null, when in fact, yeah, the real effect exists. The null is false, so we should reject it. That's great. And power, again, is 1 minus beta, or beta is 1 minus power. They're opposites of each other. So again, just to hammer this lesson home, the word error, when we talk about type 1 and type 2 error, does not mean you screwed up. It just means you made a good bet. You did the stats properly. You followed procedure. But just due to random chance and probability, your bet happened to turn out wrong this time. You cannot avoid that in science. Okay? So you made a good bet, just turned out wrong this time. Oh well, you should still do it that way in the future. But that also means when we do a statistical test, we do not know whether or not we made an error like this. We have no way to know what the reality is unless we, magically can measure the entire population. We only have access to our sample information and whatever probability theory allows us to infer from that, which is going to be probabilistic. But we can choose our alpha level and we can affect our power, and thus our beta level, so we can have a good idea what the odds of a type 1 and a type 2 error are. Alpha, we know it exactly since we chose it, and beta, we can estimate and we can make it better with things like a big sample size. Okay, we'll stop here for now, but hopefully you've gained a deeper appreciation for the fact that scientific practice using statistics always involves some uncertainty. Hopefully that means that you treat any results, especially new results that haven't been replicated yet, with a little bit of intellectual humility. But also, I hope you begin to see how we can estimate and quantify things like power of a study based on its design and its sample size, so we can actually judge how good a study is, how likely it is to avoid type 1 and type 2 errors, and this can make you a more critical and thoughtful consumer of scientific research. You might also see why a research design that decreases variability, like a within subjects design, has some real benefits, like improving power. And also, now you'll appreciate why exactly we tend to emphasize using a large enough sample size. And indeed, there are ways to actually calculate how big of a sample you'll need to get the desired power level for your study that you want by doing what's called a power analysis. So that means instead of just intuitively trying to guess whether 15 or 20 or 50 or 80 or 150 is too small of a sample size for a given study, humans are bad at that intuition. We can't guess that just by seeing the sample size of a study and being like, oh, that feels small to me. But you can actually calculate that stuff out, the power analysis, and answer it more objectively.